Dear students, today we are going to see page replacement algorithm. So first of all, what is a page replacement algorithm and why is page replacement algorithm needed? We all know that whenever the CPU needs to execute a particular data, the data which is present in the secondary memory or the virtual memory should be loaded to the main memory or the physical memory. So the physical memory is very small in size than the virtual or the logical memory. So there won't be enough space sometimes for loading new pages. So whenever CPU requests for a page, first of all we check the physical memory. If the page is present in the physical memory, the data or the page is present in the physical memory, that is called a page hit. So page is present in the physical memory. We need not do anything. Directly the page can be accessed from the physical memory. But sometimes when we check in the physical memory, the page will not be present in the physical memory. That is called page fault or page miss. So page hit is there and page miss is there. Whenever the page is present, we call it as page hit, and whenever the page is not present, it is page fault or page miss. So whenever page miss occurs, we need to load the corresponding page to the physical memory from the logical memory. If there is no free frames available in the physical memory for loading this new page, we need to replace or remove some of the existing pages in the physical memory so that the new page can be loaded into the physical memory. This is where page replacement comes. If there is no enough space in the physical memory for loading a requested new page, some pages from the physical memory should be removed using some criteria. So these criteria is given by different replacement algorithms. So whenever we remove a page from the physical memory, that page is called a victim page, which will be swapped out to the virtual memory or the logical memory, and to its place a new page, a requested page will be loaded. So we have three page replacement algorithms. So page replacement algorithms are used for finding the victim page that can be swapped out from the physical memory so that we can make room for a new requested page. So first page replacement algorithm is FIFO or first in first out page replacement algorithm. First in first out, as the name suggests, the page which is in first will be out first. So that is FIFO, first in first out. It maintains the character of a queue in which the page which stands first in the queue will be going out first. It is the simplest page replacement algorithm. So we'll see this how FIFO works with an example. So assume this is a reference string, this is the requested page numbers, and we consider that we have a physical memory with 3 frames. The structure of physical memory, we have only 3 frames in the physical memory. So this is our physical memory with 3 pages. Initially all the 3 pages will be free. So we'll see how the reference string will be handled. So first requested page is 1. Initially all the frames in the physical memory are free, so 1 can be accommodated. So first of all we'll check whether 1 is present in the physical memory. 1 is not present in the physical memory, which means we have a page miss. Page miss is there, page is not there. So this particular page number 1 should be loaded from virtual memory. So we can load and keep the page number 1 in the physical memory. So there is no problem. We need not do any replacement as there are free frames available in the physical memory. So 1 is stored. We have a miss, but no need of replacement. Again now this is the physical memory frames status. Next request is for page number 3. Again we will check whether the page number 3 is present in the physical memory. It is not present. If it is not present, it is called a miss. The page should be loaded to the physical memory, but as there are spaces available, free spaces available in the physical memory, we need not do replacement. So again this 3 is stored into the physical memory. So next requested value, again now we have 1 and 3 and 1 free space in the physical memory. So next request is for 0. 0 is not present in the physical memory, so again it is a miss, but no need of replacement. We can directly store 0 to the physical memory. So again now 1, 3 and 0 are stored in the physical memory. No free spaces are available. Next requested value is 3. So we'll check whether it is present in the physical memory. It is present in the physical memory. Then it is called a page hit. So whenever page hit happens, nothing has to be done. The page can be directly accessed from the physical memory and executed. So again next we have 1, 3 and 0. The requested page is 5. We check in the physical memory. The requested page is not available, which is called a page miss. So we need to load the page. But there is no space, there is no free space in the physical memory. In this case, one of the pages which is already stored in the physical memory should be swapped out so that 5 can be swapped in. So we need a replacement here. Replacement is needed. So we are using first in first out. In first in first out, the oldest page that was int to the physical memory will be removed. Which is the oldest page that was int? Oldest page is 1. So 1 will be swapped out and 5 will be swapped in. So this is how the replacement is done. 1 is swapped out and to 1's place 5 will be swapped in. So the physical memory will be 5, 3 and 0 after this miss. Again the next requested page is 6. We'll check whether 6 is present. 6 is not present, so it is again a miss. We need to load the page, but there is no free spaces. So again we need to go for a replacement. So again we check which among the 3 is the oldest one that was int. The oldest one is 3. 3 was the oldest one which was int. So we'll swap out 3 and swap in 6 so that 6 can be executed. So now the physical memory will have 5, 6 and 0. Again we go for the next request. Next requested value is 3. 3 is not present in the physical memory, so it is a miss and we need a replacement as there is no free spaces. So again we check for the oldest page. The oldest page which was in among 5, 6 and 0 is 0. So 0 will be swapped out and 3 will be swapped in. Again the physical memory will have 5, 6 and 3. Next request is for 5. 5 is already present in the physical memory, so it is a page hit and we need not do anything. This is how FIFO algorithm works. Whenever a page fault occurs and a page replacement is required, we swap out or we replace the new page with the oldest page that is present in the physical memory. So this is the first method, FIFO. Now we will go for the second method. Optimal page replacement algorithm. Optimal page replacement algorithm. Optimal page replacement algorithm is actually an ideal algorithm which is very impossible to implement. It is impossible to implement because according to optimal page replacement algorithm, the page which will be least used or which will not be used for a longer period in the future will be replaced, which is impossible to identify in a real time. So the page which is used, which will not be, which is not used for a longer period in the future needs to be removed. So we cannot identify this page which is not been used for future for a long time. So that is why it is impossible to implement, but theoretically it is a perfect algorithm for page replacement. So again we'll take the same example and see how optimal replacement algorithm works. So we have the same reference string. Initially the first few steps will be same for all the algorithms. So first, initially all the 3 frames in the physical memory are free. First requested page is 1 is not present in the physical memory, so it is a page miss or page fault. So we loads the page number 1 to the physical memory. The next request, when the next request comes, we have 1 in the physical memory and 2 free frames. Next request is for page number 3. Page number 3 is not present in the physical memory, so it is again a miss, and page number 3 is loaded into the physical memory. Next we have 1, 3 and 1 free space. The next requested value is 0, which is not present in the physical memory, so again a miss, and we will load the page number 0 to the physical memory. So these 3 steps are similar to FIFO. In the 4th step, 1, 3 and 0 is already present, and the requested value is 3, which is already present in the physical memory, so we need not do anything. It is a page hit. We can directly access. Going to the next request, we have 1, 3 and 0. The next requested value is 5. So we'll check 5 is not present in the physical memory, so it is again a miss or page fault, where we need a replacement because there are no free frames available for loading page number 5. So here we have to go for replacement. Now in optimal replacement, how we will identify the victim page? So we have to find the page which is not being used for a longer time in the future. Future means after 5 it is not being used. So we have to consider the values in the reference string which are to the right of the current request. So after 5, among which of this is not being used for long time? So 1, 3 and 0, actually 1 is not being used for a longer time, 3 is used, 0 is not being used. So we can take either 1 or 0 from the physical memory. So now if consider we have the reference string with the value 0 also with it. In this case 3 and 0 are being used in the future, but 1 is not being used. In that case 1 can be swapped out. So let's say 1 can be swapped out and 5 can be swapped in. So the new values will be in the physical memory will be 5, 3 and 0. Again the next requested value is 6. 6 is not present in the physical memory, so again a miss, and as there is no free spaces we need to replace something. So again we'll check which is the one, which is the page which is not being used for a longer time in the future among these 3. So 3, 5 and 0. Among this, 0 is the one which is not been used for longer time. So we'll swap out 0 and swap in the newly requested page 6. So again we have 5, 3 and 6 in the physical memory. Next request is for 3. So 3 is already present in the table. So it is page hit. We can directly access. Again for the next one, 5, 3 and 6 is present. Next request is for 5 which is already present. So again it is a hit. Then the last requested value is 0. What we have in the physical memory is 5, 3 and 6. So 0 is not present. So what we can do? We have to replace any one of this so that 0 can be accumulated. In this case, as we don't have any future reference strings, we can say that any one of this can be replaced and 0 can be included into the physical memory. So this is the second one. The third replacement method is LRU, least recently used page replacement, in which the least recently used page is replaced whenever a replacement is needed. So we'll go for the same example. First 3 steps are same. We have an empty physical memory. First request 1, 1 is not present, so it is a miss. 1 is loaded into the physical memory. Next one, we have a 1 already. Then we'll get a new request for page number 3. 3 is not present, so it is a miss. And we need to load 3 into the main physical memory. Next request is for page number 0. We have 1 and 3 already. 0 is not present, so again a miss, and we will load 0 to the physical memory. Next request is for page number 3. Already we have 1, 3 and 0 in the physical memory. So 3 is present, so it is called a hit. So in all the 4 steps, we need not do any replacement. Now we have 1, 3 and 0. Next requested page is page number 5. Page number 5 is not present in the physical memory, so it is a miss. And as there is no free frames, we have to go for replacement. So in LRU, the least recently used page will be replaced. Which is the least recently used page? So before, this is the current request. The previous request was 3. It is the recently used value, recently used page. This one is the next recently used page. So least recently used page will come to the left side. So 1 is the least recently used page in this context. So 1 will be swapped out and 5 will be swapped in. So next we have a new request. So now our physical memory will have 5, 3 and 0. The next request is for page number 6. Page number 6 is not present, so it is a miss again, and we have to go for replacement. Again, which is the least recently used page. We have 5, 3 and 0 in the physical memory. Among these 3, which is the least recently used? So 5 is most recently used, 3 is the next recently used, and 0 is the least recently used. So here 0 will be swapped out and the requested page 6 will be swapped in. Again, now we have 5, 3 and 6 in the physical memory. Next request is for 3. So 3 is already present in the physical memory, so it is a page hit, so we can directly access the page. Again, the same values will be stored in the physical memory, 5, 3 and 6. Next request is for page number 5. Page number 5 is already present in the physical memory, so again it is a hit. Next request is for page number 0, which is not present in the physical memory, so we need to do a swap in and swap out process. So we'll see which among this is the least recently used, 5, 3 and 6. So 5 is recently used, 3 is the next recently used and 6 is the least recently used. So 6 will be swapped out and 0 will be swapped in. So this is how we handle the page replacements in operating system.